Okay? So because our fundamental particles act like little magnets, have a magnetic moment as an intrinsic property of the particle, then when we put those together to form atoms, some of them act like magnets. When we put those together to form a chunk of iron, sometimes that chunk of iron acts like a magnet. And we talked about the fact that the Earth's magnetic field has flipped a number of times over the years. And the reason we know that is because as the molten Earth, right, evolves, it comes out of the crust in gaps under the oceans, right, where the molten magma comes out from the Earth and forms along the ocean floor. We can see that the magnetic moments of the iron, the particles in that material, what happens? They act like little magnets, right? So they want to align themselves with the Earth's, with the strongest magnetic field in the area, which is the Earth's magnetic field. So they align themselves with the Earth's magnetic field, and then that cools, and they form in that orientation. And then if the Earth's magnetic field flips, they would align themselves, as the plates shift under the ocean floor and more, magma when it's liquid still? I think so. I have to ask my 5th grade son. They're learning that now. As the stuff comes out, then it aligns with the Earth's magnetic field that has shifted or reversed since the previous material formed. And so you can see these reversals in the material as it forms, or sedimentary material that's forming a mountainside, things like that. And the Earth's magnetic pole reversal is visible there. It's not very consistent, roughly every 250,000 years, but it's not very consistent. The sun's poles reverse very consistently. I think it's every 11 years. Okay. Permanent magnetism, ferromagnetism, because this is a property of iron and the iron atom, permanent magnets, and that's about what I want to cover for ferromagnetism and permanent magnets. Okay, so I want you to have a picture of why a chunk of iron sticks to a magnet, and I think now you can sort of see how that happens. Okay, let's talk about loops of wire and what happens when you put them together. A current carrying wire. So I'll sort of draw it. There's a loop of wire. It's perpendicular to the plane of the board here, the plane of the page. So what I really should draw it is this way. That's one side, and that's the other side. This is a cross section, and we're going to run a current around that loop of wire, which means on the left side the current is coming out towards us, and on the right side it's going into the board away from us. You see that? This is a cross section. This loop of wire is oriented like this. We've kind of chopped it in half, and we're just looking at the intersection with the page here. And the current is coming out on this side, it's looping around, and it's going in on this side, and then it loops around behind the board and comes out again, right? It's making a loop like that, the current. So what direction is our magnetic field? In the center of the loop, what direction is the magnetic field? Up. Like that, right? So let's see. There's two ways you can do this. The way we've learned already, you have a long wire carrying a current. You know that the magnetic field forms little circles around the wire, right? It encircles the wire. So what do? You stick your thumb in the direction of the current, and your fingers in your right hand wrap around the wire in the same direction that the magnetic field wraps around the wire. So on this side right here, the magnetic field goes counterclockwise, like I've sort of drawn on the blue line there. I'll draw another one. Like that. And on this one over here, it's going in, so it would form clockwise around that side. Those are the magnetic fields. And everywhere on the inside of the loop, the magnetic field would be going up, as you can see here. And everywhere outside, it would be going down. You good with that? The other thing you can do is, this is a new right-hand rule you're learning now, because 2 wasn't enough. You can just wrap your fingers around, like you're grabbing something, around the loop of wire in the direction of the current flow, and your thumb points in the direction of the magnetic moment, the magnetic field on the inside of the loop. So if you just sort of, if the current is going counterclockwise, you wrap your fingers around the loop and your thumb points in the direction of the magnetic field. But we've already learned that the current coming this way creates a magnetic field that's up out of this thing, the wire loop and the center. So either way, whichever one you prefer. So this thing acts like a little magnet, doesn't it? That's a little magnet. This is a loop of wire with current.